Décollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
NASA's James Webb Space Telescope has hardly opened its eyes, and the universe is new, more mysterious, more beautiful than humanity's dreams.
High above our planet, a sentinel of science has been silently orbiting, peering into the abyss of time and space. The James Webb Space Telescope, a marvel of human ingenuity, has just made a series of discoveries that will send shivers down your spine. Scientists and astronomers from around the world have been working tirelessly, poring over the data beamed back from this cutting-edge telescope.
That's the most exciting piece of this telescope, of this remarkable instrument we put in space, is finding things that we didn't expect, that we can't explain, because that means that we have to revise our understanding of the universe.
What they've found at the edge of the universe is nothing short of astonishing. As we gaze into the cosmic abyss, we're about to reveal the mind-boggling truths that James Webb has uncovered. So join us as we embark on a mission of cosmic proportions, where James Webb's astonishing discoveries reveal the untold secrets lurking at the very edge of the universe. The Cosmic Time Machine. The James Webb Space Telescope is an incredible accomplishment in the world of space telescopes. It's specially made for studying infrared light from space, allowing it to see far into the universe and discover objects that are very dim, very old, and very far away. According to information provided by NASA, the JWST exhibits remarkable sensitivity to infrared radiation, to the extent that it can discern even the faint thermal emissions emanating from a bumblebee, even when positioned at a lunar distance. To provide a more quantitative perspective, this astronomical instrument boasts a performance level exceeding that of the renowned Hubble Space Telescope by a factor of 100, an instrument which has admirably contributed to our understanding of the cosmos for over 3 decades. The primary objective of the JWST is to capture celestial imagery during the early stages of the universe's formation. While the Hubble telescope has delivered awe-inspiring images of the cosmos, it does possess inherent limitations, preventing scientists from gazing upon the first galaxies that emerged following the Big Bang. The JWST promises to rectify this shortfall, serving as a veritable cosmic time machine. It allows us to delve into the inaugural chapter of the universe's 14 billion-year history, a chapter that has remained elusive until now. The remarkable capabilities of the JWST enable it to record light that has traversed the cosmos for up to 13.5 billion years, effectively extending our observational window into the universe by several 100 million years earlier than what the Hubble telescope can achieve. Webb Telescope's golden mirror technology. A pivotal factor contributing to the impressive functionality of the James Webb Space Telescope is its expansive primary mirror, boasting a diameter of 6.4 meters. This mirror consists of 18 smaller segments, and it is of paramount importance that these segments achieve precise alignment. Notably, what sets these mirror segments apart is their remarkable coating of an exceptionally thin layer of gold, measuring a mere thousandth of the width of a single strand of human hair. Remarkably, these segments, adorned with less than 2 ounces of 24-karat gold, possess superior capabilities in reflecting infrared light when compared to other metals. It's worth emphasizing that infrared light lies just beyond the range of human visual perception. However, it's worth clarifying that the mirrors are not constructed entirely of gold. Rather, they are crafted from beryllium. To function optimally, the Webb telescope requires careful temperature control. Achieving this is made possible by a 5-layer sun shield, which spans an area equivalent to that of a tennis court. This intricate sun shield was folded up during the telescope's launch on Christmas Day. Remarkably, in less than 2 weeks, the sun shield's incredibly thin layers were successfully unfurled. This sun shield plays a vital role in safeguarding the telescope from the intense heat emanating from the sun, which would otherwise inundate its sensitive sensors. The side of the telescope that faces the sun must endure temperatures of approximately 260 degrees Fahrenheit, while the opposite side is cooled to an astonishingly frigid 370 degrees below zero. This results in an almost staggering temperature difference of nearly 600 degrees between the two sides. This sun shield bestows upon the Webb telescope an astonishing level of sun protection comparable to an SPF of 1 million. A million miles from help, one shot at perfection. One aspect that causes concern among scientists regarding the Webb telescope is its inability to address any problems that may arise, both during its launch and while in operation. To provide some perspective, throughout Hubble's existence, 5 space shuttle missions were conducted to correct its initially blurred vision and to perform various maintenance and upgrades. However, this was feasible because Hubble is a mere 340 miles away from Earth. In stark contrast, the Webb telescope is situated significantly farther, nearly 1 million miles distant, placing it well beyond the reach of repair crews conducting spacewalks. Therefore, NASA has just one opportunity to ensure its flawless performance. Nonetheless, if the necessary technology is developed, scientists might eventually dispatch a robot to refuel the Webb telescope, thereby extending its operational lifespan. Regarding its fuel supply, initially, NASA estimated that the telescope would only remain functional for a decade. However, due to an efficient launch, there is presently sufficient fuel remaining to power the JWST for a total of 20 years. It's fascinating to note that the James Webb Space Telescope has already demonstrated its value despite its nearly $10 billion cost, even before capturing its initial images. Northrop Grumman, the company responsible for constructing the telescope's mirrors, had to pioneer entirely new methods since creating such a precise mirror had never been attempted before. The innovative technology they devised is now even being applied by eye surgeons. In addition, Northrop Grumman made significant strides in the realm of computer technology. They achieved remarkable progress in understanding how to efficiently deploy massive objects. For instance, they mastered the art of taking a colossal sun shield, equivalent in size to a tennis court, and folding it up neatly for deployment. James Webb Telescope. Terrifying discovery at the edge of the universe. Human curiosity has always revolved around the mysteries of our surroundings. Yet, voyaging across the universe entails not only traversing vast distances in space, but also navigating the depths of time itself. Before we embark on this cosmic journey, it's essential to establish a fundamental parameter, the universe's dimensions. To pinpoint its edge, we must first grasp the sheer scope of the universe. Our universe is believed to be a venerable 30.772 billion years old, indicating its considerable age. So, just how expansive is our universe? Present-day scientists estimate its width to be 28.5 billion parsecs. To comprehend the enormity of this figure, we need to delve into some astronomical basics. To begin, let's consider the size of a parsec. To grasp the definition of a parsec, we should first acquaint ourselves with the concept of an astronomical unit, often abbreviated as AU. 1 AU represents the average distance between the Sun and Earth, approximately 150 million kilometers. Now, a parsec is defined as the longest side of a triangle, with its shortest side measuring 1 AU while subtending an angle of 1 arc-second at the opposite vertex. If we delve deeper into these calculations, we find that 1 parsec is equivalent to 3.26 light-years, which is the distance light travels in 1 year, approximately 9,460 billion kilometers. Now, consider that we are discussing a staggering 28 billion parsecs, which equates to 93 billion light-years, or an astonishing 879,780 times 10 to the power of 18 kilometers. Such a scale is nothing short of mind-boggling. To put this into perspective, if we were to stretch out the combined length of the DNA from every human on Earth, it would span a mere 0.119 billion light-years. Let us carefully examine the previously mentioned data, and you will discern an apparent incongruity. The speed of light represents the ultimate conceivable velocity. Therefore, given that the universe is estimated to be approximately 13.7 billion years old, a perplexing question arises. How can the universe exhibit a span of roughly 93 billion light-years? In principle, an entity originating shortly after the inception of the universe and traveling at the speed of light should have traversed a maximum distance of 13.7 billion light-years by this juncture, with no deviation from this value. The conundrum lies in determining the origin of all matter existing beyond this threshold. This is where we invoke Hubble's law. This law posits that objects observed in deep space exhibit a phenomenon known as redshift, wherein the wavelength of light shifts towards the longer red end of the electromagnetic spectrum. But what prompts this wavelength elongation? One fundamental factor is the expansion of space itself. It is crucial to note that this expansion extends beyond mere object separation. It encompasses the very fabric of space. The intriguing aspect of this phenomenon is its acceleration, attributed in part to the influential presence of dark matter and dark energy. Consequently, when calculating the universe's dimensions, we must factor in the additional distance resulting from the expansion of space. Consequently, the boundary of the universe is not confined to a mere 13 billion light-years from Earth, but is extrapolated to extend far beyond this point. Chasing light beyond infinity. One notable phenomenon within the universe is the existence of objects that may forever remain beyond our visual perception. Why is this the case? The answer lies in a staggering distance of approximately 16 billion light-years from Earth, which marks the current cosmic event horizon of our universe. At present, we have not yet reached this threshold. This distance serves as the utmost boundary for light to reach us if it were to originate from that distant point today. Consequently, this implies that beyond the 16 billion light-year mark, the expansion of space outpaces the speed of light itself. Light will never reach us from such distances due to its journey through continuously expanding space. Additionally, this realization underscores the fact that any events occurring today beyond the cosmic event horizon will forever elude our observational capabilities. However, it's important to note that we can extend our observational reach even further through advanced telescopes like the JWST. The GNZ-11, the most distant galaxy ever observed, is situated at an astonishing distance of approximately 32 billion light-years from Earth. Importantly, this measurement accounts for the ongoing expansion of space. The surface of last scattering. Approximately 46 billion light-years away from Earth lies a cosmic phenomenon known as the surface of last scattering. This intriguing entity manifests itself uniformly, presenting an observable consistency regardless of the direction in which it is observed. The surface of the last scattering can be likened to a spherical shroud of mist, serving as the birthplace of the initial photons composing the cosmic microwave background radiation. These photons emerged following the processes of recombination and photon decoupling. Despite its name, this locale signifies the inaugural encounter of light scattering, yet it represents the ultimate limit of our observational capabilities. Is this indeed the outermost boundary of the universe? The answer is a nuanced one. This location technically represents the utmost spatial and temporal extent that falls within our observational purview. In essence, it constitutes the periphery of what we term the observable universe. Beyond this threshold lies a domain known as the opaque universe. This demarcates the furthest reach of our observations, but not the limits of our imaginative capacity. Let us now venture past the confines of the observable universe. What might conceivably exist in this uncharted territory? Until now, our explorations have been confined to the ancient annals of spatial points. Yet, a more extraordinary query beckons. What potential entities could currently occupy this region? The boundary of the observable universe also signifies the particle horizon, delineating the farthest distance from which we can glean insights into the past. All that we have thus far beheld has been contextualized through the prism of Earth as our reference point, wherein the passage of time is scaled with increasing spatial separation. This prompts us to ponder. Does the universe possess an infinite expanse? According to Einstein's theory of relativity, a universe with a flat topology implies infinitude. However, can we definitively assert the absence of any discernible edge or culmination of the universe? The answer to this query is not straightforward. Our investigations have yet to furnish conclusive evidence concerning the finite or infinite nature of the universe. A gaze into the gravitational distortion. A relatively small section of the celestial expanse is observed by the JWST Deep Field, which centers its attention on the galaxy cluster referred to as SMACS 0723. Notably, SMACS 0723 is located at an astonishing distance of 4,600,000,000 light-years away. The intriguing aspect of this observation lies in the profound influence exerted by its powerful gravitational field on galaxies positioned even further behind it. These background galaxies experience substantial distortion, often manifesting as expansive arcs in regions of maximum gravitational force. In a remarkable instance, it has been calculated that light emitted from a remote galaxy required a staggering duration of 13,100,000,000 years to traverse the vast cosmic expanse and reach the JWST's telescope. This phenomenon occurs due to the stretching effect that the light undergoes over time as the universe itself expands. Owing to their immense remoteness, the primary target galaxies observed by the JWST have had their visible light, originating from their stars, stretched into the infrared spectrum. Astronomers can now compare JWST observations to Hubble's images of nearby galaxies. This data helps us understand how galaxies evolved, forming the structures we see today. The JWST's quick deep field image, captured in hours, revealed many galaxies. It often observes galaxies, with galaxy clusters acting as natural magnifiers. Scientists used the JWST to study 55191, two galaxies. They're investigating how one galaxy's light changes as it passes through the other, which will reveal details about dust in the intervening galaxy. Galactic waltz.
All these little dots are stars?
All these little dots are galaxies, some of which are bigger than Earth.
Galaxies and black holes caught the telescope's attention when it first snapped pictures. Among these, there was a closely knit gang called Stephan's Quintet, made up of 4 galaxies engaged in a gravitational waltz due to their proximity. The 5th galaxy in this group seems nearby, but it's much closer to us and happens to line up with the others in our line of sight. Together, these 4 mingling galaxies form a special playground for astronomers to study how galaxies interact and eventually merge. Such mergers were likely pretty common in the early universe, and played a big part in creating the massive galactic structures we see today. They're also thought to be connected to the growth of supermassive black holes, each of which hangs out at the center of a galaxy. The JWS took a look at Stephan's Quintet using its NIRCam and MIRI sensors. MIRI's pictures in particular surprised astronomers because they revealed unexpected shapes of the galaxies. MIRI's clarity on the phantom galaxy. The MIRI instrument achieved something truly remarkable when it studied the phantom galaxy M74. This spiral galaxy resides a staggering 32 million light-years away from Earth, and it's positioned directly in our line of sight. Its captivating spiral arms, which are the defining features of spiral galaxies, have long captivated the interest of astronomers. However, until now, these arms have never been observed with such clarity. For the very first time, we can see these spiral arms where stars are actively being born, extending into the core of the galaxy. Collaboration plays a vital role as we combine fresh telescope observations with data from other observatories. This collaborative effort will deepen our comprehension of the celestial objects under scrutiny, potentially leading to exciting discoveries. Infrared astronomy, a speciality of the JWST, holds a unique advantage. It enables us to peer deeply into regions where stars are forming because infrared light, characterized by longer wavelengths, is less affected by dust, molecules, and atoms. This remarkable feature makes objects that typically obstruct our view of stellar nurseries nearly transparent, allowing us to study the life cycle of stars with greater clarity. Another image captured by the JWST brought us closer to CAM's observation of the star-forming region known as NGC 3324. Which is situated approximately 7,500 light-years away within the Carina Nebula. This nebula, primarily composed of gas and dust sculpted by the influence of starlight, resembles a breathtaking natural landscape. What's truly astonishing is the use of infrared technology to unveil this once-hidden world, now displayed in all its magnificent splendor. Originally referred to as the cosmic cliffs, this extensive expanse of gaseous cliffs bears a resemblance to a mountain range and serves as the boundary of a vast cavity sculpted by the intense ultraviolet radiation emitted by young stars. Star factories of the Tarantula Nebula. The Tarantula Nebula, found in the Large Magellanic Cloud, is a distant galaxy situated hundreds of thousands of light-years away from our own Milky Way. It's like a completely different celestial neighborhood. Despite its far-off location, the Tarantula Nebula is remarkable because of its enormous size and the large number of stars being born there. Many of these newly forming stars are much bigger than our own Sun. One important thing to note is that the JWST is equipped with a range of infrared instruments. Infrared light has a special quality that allows us to see through the usually obstructive effects of gas and dust that surround places like star-forming regions. While the Hubble Space Telescope might show these regions as blurry patches, the James Webb Telescope can cut through this dust and reveal the actual process of star formation happening inside these cloudy cocoons. In this specific image of the Tarantula Nebula, you can make out various knots and areas where new stars are taking form. Infrared technology lets us see through the surrounding gas and dust, providing glimpses of protostars emitting radiation that pushes away the nebular material, slowly revealing these baby stars. As time goes on, these massive, dust-filled spaces will expand, gradually uncovering all the stars that are being born within them. What's truly impressive is that this image is available in high resolution, with a remarkable resolution of 14,000 by 8,000 pixels. Although it was one of the first images captured by the JWST, astronomers initially chose to share the image of the Carina Nebula first, and kept this gem of the Tarantula Nebula for a later reveal. The universe hides its secrets in the vastness of time and space. But with the James Webb Telescope, we've taken a giant leap into the cosmic unknown. Now, imagine this. How far does the universe stretch? Could its edge hold something unimaginable? Our universe, ancient at 13.772 billion years, seems boundless. Scientists tell us it's a staggering 28.5 billion parsecs wide. What's a parsec? Well, it's 3.26 light-years, or about 9.46 trillion kilometers. Yes, it's huge, but consider this. We're talking 93 billion light-years. That's 879 sextillion 780 quintillion kilometers. Here's the puzzle. Light, the universe's speed limit, couldn't have traveled this far in 13.7 billion years. So what lies beyond? Enter Hubble's law. Objects in deep space show redshift, a sign of the universe's expansion. It's not just things moving away, it's space itself growing. The expansion, driven by dark matter and dark energy, pushes boundaries. But wait, beyond 16 billion light-years, light can't reach us. An eternal darkness. Or can it? James Webb Telescope, with its extraordinary reach, glimpsed the GNZ11 galaxy at 32 billion light-years. So, what's out there? Can we uncover the universe's deepest secrets? In the cosmic abyss, the universe keeps its horrors and wonders. With James Webb, we're reaching further than ever before. What terrors and marvels lie beyond? And can we ever truly grasp the universe's darkest mysteries? Let us know what you think in the comments below. The star with a story written in rings. The Orion Nebula holds a special place as maybe the most famous spot where stars are born, and that's probably why it's so well known. That's why astronomers decided to point their telescope in that direction. Now, the Orion Nebula is something you can see in the night sky without any fancy equipment, especially if you're lucky enough to have a clear, dark sky. And if you've got some binoculars or a small telescope handy, you're in for an even more amazing view. Specifically, what we're checking out here is called the Orion bar. When we look at the pictures taken by the JWST and compare them to the ones Hubble took, we see a big difference. Take a good look at those bright stars and how precisely they're lined up. This comparison shows how much better the JWST is at taking pictures compared to the Hubble. Both telescopes show the major stuff, but the JWST gives us a much clearer and sharper picture. all thanks to its impressive 6.5-meter mirror, which is way bigger than Hubble's 2.5-meter mirror. One of the most interesting images from this year shows a Wolf-Rayet star known as WR140. These stars are newly formed and extremely hot, emitting a tremendous amount of radiation. When astronomers first looked at a picture of this star, they saw something very unusual: concentric rings surrounding it. Surprisingly, these rings are not a mistake or distortion in the image. They are very real. They exist in the material that surrounds the star in the form of a nebula. Here's what's going on. The star has a companion in a binary system. The star throws out material into the cloud or nebula that surrounds it. As the companion star moves through this material, it carves out rings, one after another. It's somewhat like counting the rings in a tree to determine its age. In this situation, each ring represents approximately 8 years in the star's life cycle. What adds to the fascination is that the binary companion orbits the star every 8 years, so each ring serves as a record of 8 years' worth of changes in the life of this young star. Pulsations of creation. The JWST has illuminated the process by which stars progress through their life cycles. Stars similar to our Sun, for instance, undergo a transformation where they grow into red giants before eventually shrinking down into white dwarfs, essentially turning into the remnants of stars. During this contraction, they release their outer layers, forming what scientists call a planetary nebula, although this name doesn't quite capture the phenomenon precisely. The JWST's image of the Southern Ring Nebula vividly illustrates this fascinating process. The star goes through a repetitive cycle of expelling layers of material from its outer shell over thousands of years as it changes into a white dwarf. The remaining core of the star then starts to compress and heat up, beginning a new phase of energy production and pulsations. Each pulsation results in the expulsion of another layer of material. This cycle continues indefinitely until there is simply not enough material remaining to sustain the pressure of the core and trigger nuclear fusion. At this point, the star becomes a white dwarf. Interestingly, our own Sun is destined to follow this same fate in roughly 4.5 billion years. Unveiling alien atmospheres. The JWST has a key mission: to study planets in different stages of development, from newly forming ones to mature planets around distant stars. Using its special infrared abilities, the telescope can see through the clouds of gas and dust around star-forming areas. This helps us watch as new planets form around emerging stars and allows scientists to study a planet's atmosphere separately from its host star. Astronomers aim the JWST at a star where they expect a planet to pass in front of it from our view, called a planetary transit. The telescope captures images of both the star and the planet during this transit, revealing details about the planet's atmosphere. For example, it discovered carbon dioxide in the atmosphere of WASP 39b, a planet about 700 light-years away. This was the first time carbon dioxide had been found on another planet, along with other substances like water vapor, potassium, sodium, and carbon monoxide. The TRAPPIST-1 system is exciting for space enthusiasts. It has 7 Earth-sized planets orbiting a red dwarf star, with some in the habitable zone where life-friendly conditions could exist. Webb is studying these planets, examining their atmospheres. So far, it has looked at 2, TRAPPIST-1b, which is airless like Mercury, and TRAPPIST-1c, which was hoped to resemble Venus but also lacks an atmosphere. There are still 5 more planets in this system to investigate. JWST's cosmic magnifying glass. The JWST isn't just powerful by itself, but it becomes incredibly effective when it lines up with a gravitational lens. This unique setup uses the gravitational pull of a whole cluster of galaxies as a natural lens, allowing us to make much more precise observations of objects beyond this lens. These observations uncover details about the substances present in these far-off galaxies that would be otherwise hidden using the telescope's regular abilities. Additionally, this arrangement offers some extra benefits. In a particularly noteworthy case, James Webb identified multiple instances of the same supernova event within a galaxy. This happens because the light from the supernova follows different paths around the gravitational lens formed by the galaxy cluster. Consequently, astronomers witnessed the same Type 1a supernova event occurring multiple times, depending on the various routes the light took around the intervening galaxy. The potential of using a galaxy cluster's gravitational pull as a natural telescope is truly astounding. It allows us to observe objects with magnitudes of clarity tens of thousands of times greater than relying solely on the telescope's capabilities. While we're still grappling with the mystery of dark matter, it's astonishing that we can use it as a tool for scientific discovery. The cosmic vacuum cleaners. The JWST is currently engaged in an ambitious observational campaign known as JADES. This initiative bears a resemblance to the renowned Hubble Deep Field, albeit with a specific focus on a distinct region of the celestial sphere. Extensive research efforts have been dedicated to scrutinizing this designated area, with plans for even more comprehensive investigations in the future. One remarkable achievement of the JWST is its capacity to unveil a staggering tenfold increase in the number of observable galaxies and deliver 15 times greater resolution compared to the Hubble Space Telescope. This impressive feat is accomplished through a technique known as spectroscopy, wherein the incoming light from distant celestial objects is dispersed into a spectrum of colors resembling a rainbow. Scientists then scrutinize distinctive spectral lines to ascertain the composition of cosmic entities. Of particular significance is the discovery of organic materials within a remote ancient galaxy, akin to residues left behind after a chimney fire. This discovery holds profound implications, as these organic compounds are believed to be potential precursors to life, offering invaluable insights into the origins of life on Earth. The JWST's scientific pursuits extend beyond the study of galaxies. It also conducts observations of supermassive black holes known as quasars. These astronomical behemoths resemble cosmic vacuum cleaners, voraciously consuming matter and emitting extraordinarily intense radiation. Notably, the JWST identified one such quasar, denoted as Sears 1019, with a mass 9 million times that of our Sun, an existence dating back to the early epochs of the universe. This revelation challenges previous assumptions about the rapid growth of black holes during that era. Conceiving the universe as a vast, interconnected network, akin to a sprawling cosmic web comprising galaxies and galaxy clusters interconnected by tenuous filaments and voids, the JWST has provided valuable insights into the nascent stages of this cosmic structure. Observations have revealed a substantial galaxy exerting a magnetic pull on smaller neighboring galaxies, culminating in the formation of an extensive galaxy filament stretching across 3 million light-years. Notably, this phenomenon occurred when the universe was a mere 830 million years old, granting us a rare glimpse into the conditions of that distant epoch. Do you think the James Webb Space Telescope's findings will change our perception of the cosmos? Let us know what you think in the comments below.